So when you have something going around a circular path, there's two velocities to consider. One is, suppose that you were standing in the middle and you were watching as somebody runs around, maybe put it like this, and you're watching as somebody runs around this circular path. Then how fast do you, as standing in the middle, how fast do you have to rotate? Now the person that's out here running, as they're running around this circular path, how fast are they running? Well, the person in the middle, that's the angular velocity. So as they look at the person that's running, they see him right here, and then later, they're going to see them right there. So this angle, theta, is going to be changing as they're watching the person run around the circle. That's angular velocity. Linear velocity would be how fast they are running around the path like this. Now you might be thinking linear, doesn't that mean line? Well, you could think of this like a wheel, and you attach it to a car, and even though the wheel is going round and round, the car is going to be going in a line. Okay, so for angular velocity, and velocity is just another word for speed or rate, the angular velocity. So first of all, the symbol for it is like a curly W, that's called an omega. And you just need to know what's the angle, so how far did this rotate, and divide that by time. That's it. Now for linear velocity, so the person goes from this point to this point over some interval of time. Well, this red arc right here, we use S for arc length, you may remember. And if you're dealing with radians, it's just R times theta. So for linear velocity, which we use a V for velocity, you could say it's the distance over the time, or you could replace the S with the R and the theta divided by time. So this could be in feet per second, or perhaps miles per hour. This would be in either degrees per time or radians per time. So it could be in radians per second, degrees per second, but this one over here, that one has to be in radians. And then finally, if you look at this formula where all I did was replace S with R times theta, well, if you look at this part, that is that. So yet another way to do linear velocity is that it's the R times the omega. Okay, now for some examples. So this object is going around a circle and the radius is 3. All right, 3 feet. And then the angular velocity is pi over 3 radians per second. So how long will one rotation take? So pi over 3, if you were to change that to degrees, that would be 60 degrees. So one way to look at it is if it goes from here to here, that would be 60 degrees. And how many times does it have to do that? Excuse me. Until you get 360 degrees. So in other words, there's some number times 60 degrees that will equal 360 degrees. And then you can divide both sides by 60. And n is equal to 6. So it's going to take 6 of these in order to go around once. Now each one of those is going to take 1 second. So it's going to have to do it 6 times. Each time takes 1 second. So that means it's going to be 6 seconds. Now if I would have done the same thing with radians, it would have looked like this. So how many times do you have to do pi over 3 until you get a full circle, which is 2 pi? And then with this one, what I would do is multiply by the reciprocal, 3 over pi. And then the pi's can cancel and it just leaves 2 times 3 is 6. So you get the same thing, 6 seconds. One of the great things about math, you can do things in different ways and get the same answer. Then on to part B. Find the linear velocity. Well, for that, we're going to need to know the radius. So that was given to be that r equals 3 feet. That was given right up there. So it's 3 feet. And then for linear velocity, I could use any of these formulas right here. Well, the angular velocity is already given. That is the pi over 3. And the r is already given. So all you have to do is multiply them. So the linear velocity will be the r times the omega. So linear velocity will be 3 and then times pi over 3, which reduces to be nicely, that's just pi. And this is in feet, and that's in seconds, so it's going pi feet per second. Or in other words, approximately 3.14 feet every second. Then for example number 2. Suppose that you've got like a Honda or something like that. So this car, the tire or the wheels have an 11-inch radius. So how fast is the car going? If the tire rotates 2.5 times per second. All right, so the radius is 11 inches. How fast is the car going? So that's asking for linear velocity. And there's a couple of ways we could do this. One is it could use the formula that it is S over T. So the T would be per second. And then what is the S, the distance? Well, it's going to rotate 2.5 times. So that means that we could use The circumference formula is 2 pi times the radius, and then it's going to do two and a half of these. So the circumference would be 2 pi times an 11, and then multiply both sides by 2.5 because it rotates 2.5 times. So how much is this? So 2.5. Let me clear out some of this stuff. 2.5 times 2 pi times an 11. So that would be the S, the arc length. So how far did it go around the outside? After 2.5 revolutions, it's 172.788. And this is in inches, so this is in inches. And it's doing that per second, so every 1 second. So this car is traveling almost 173 inches a second. What do you think? Should they get a speeding ticket for that? What if we change this to miles per hour? So 172.788. This is in inches per second. And then there is 1 foot for every 12 inches. And then, time for the red pen, inches cancel. And for every 1 mile, there's 5,280 feet. And black pen, red pen, those cancel. And then for seconds, well, there's 60 seconds in a minute, and then there's 60 minutes in an hour. So that means that for every 1 hour, there's 60 times 60 seconds. And then, black pen, red pen, those cancel. And now it's in miles per hour. So on the top, I just need to know what is the 172.788, and then times 60 times 60. Oh, I hit times twice. Times 60 times 60. And then divide by both a 12 and a 5280. So let's see, are they going to get a speeding ticket? They're going about 9.8 miles an hour. So I don't think they're going to get a speeding ticket. Miles per hour. There it is, miles per hour. There it is, inches per second. All right, example number 3. So for example number 3, let's say that right here is the sun, as in S-U-N, not my son S-O-N, but the big ball of fire that we can see in the sky. And then somewhere out here is Earth. And as the Earth goes around the sun, we actually make an ellipse or an oval shape. But it's very close to a circle. Okay, that's sort of a sloppy circle. But anyway, it's very close to a circle. So we can use this to estimate how fast is Earth going. So you then just Google up how far away is Earth from the sun, and we are 93 million miles away. Just think, the thing that gives us light, heat, and energy, keeps us alive, is actually 93 million miles away. Okay, so basically we now have the radius. And then part A, find the angular velocity. In other words, if you were standing on the sun, be careful, it's a little bit hot, and you're watching Earth go around then how fast do you have to spin around? Well, for the Earth to go around the sun, that's 1 year. Now, we usually say that there's 365 days in a year. It's actually 365.24 or something or other. I'm just going to go with 365. I put of, or 365 days. Now, for us to go around, that would be one complete circle, which means that the angle would be 2 pi. So the angular velocity will be 2 pi divided by 365, and then this would be in radians per day. And a 2 is not going to reduce that, so it's actually done. And then part B, find linear velocity. So as we are sitting here on Earth, and if you look at a tree, or if you look at, for example, there's a wall to my right, there's a piece of paper right here. We're not moving, we're just sitting still. There is no velocity. So Einstein had this idea that velocity, you can't just say velocity. There is no absolute velocity. So like this piece of paper, it's not moving compared to me. So the two of us, we are not being separated. There is no velocity. So for the Earth, how fast is it going? Related to the sun. So find the linear velocity of Earth relative to the sun. And I think in English you're not supposed to capitalize Earth and sun, but I've got so much respect for both of them, I am going to capitalize. Well, with linear velocity, we could use the formula that it's r times omega, because that would be a good idea since we already have the omega right there. And so it's going to be, the radius is 93 million miles, and then times the omega, 2 pi over 365. So how much is that? 93 with 1, 2, 3, 4, 5, 6 zeros. Multiply that with 2 pi getting divided by 365. So that equals 1, 6, a couple of zeros, a 921.188. So that's 1.6 million, and then this is in miles, and this is in days. Because of this being per day because of the 365. So believe it or not, we are traveling 1.6 million miles every day. I don't even get tired. Let's see, that's miles per day, and there's 24 hours. So if you divide that by 24, that's how fast we're going. Right now, you and I are traveling at 66,000 miles an hour. I don't even feel it. It's not even messing up my hair. So relative to the sun, or how fast are we going around the sun? We're going around at 66,705 miles an hour. Good job, everybody. Hold on to that Earth.